I want to look at two colligative properties that are related to each other, and that's boiling point elevation and vapor pressure lowering. Remember that both of these are related to the transition of a solvent from the liquid to the gaseous phase, and we'll get quantitative descriptions for these in this video. So first off, boiling point elevation. And remember, we talked about the underpinnings of this before, but the idea is that the boiling point of a solution is higher than the boiling point of a pure solvent, and star means pure solvent. Why is this? Well, in solution, the solute and the solvent have favorable interactions with each other. And if a solvent wants to boil and go from a liquid to a gas, it has to leave behind those favorable interactions with the solute. And that costs energy, which means that it's a higher boiling point. When we want to make this quantitative, we use what's called a boiling point elevation constant, kappa B, right? So BP elevation constant. Sometimes this is called an ebullioscopic constant because ebullioscopic is about boiling. And it has units of degrees Celsius per mole. What else do we need? We need the total molality. So the molality of the solute times the number of particles it forms in solution. And together, that gives us the change in boiling point. What I want you to remember is that because boiling point goes up, the boiling point of a solution equals the boiling point of something pure plus the delta T. Remember, this equation calculates the change. It doesn't calculate the new boiling point. It calculates the change in the boiling point. Let's give it a try. So here's a simple boiling point elevation calculation involving ethanol. And the way that this is written, I can tell that ethanol is the solvent. Why? Because I know its boiling point. So I know that T star equals 78.5 degrees Celsius. What I don't know yet, of course, is the boiling point of the solution. But I do know that I have a solute, right? My solute is 6.4 grams of vanillin in 50 grams of ethanol. And ETOH is just an abbreviation for ethanol. So I have my equation, of course, my delta TB equals kappa B times M. So let's go ahead and assign things. I know that my kappa B is 1.22 degrees Celsius per mole, which means that I need to now find the molality of vanillin. And because I didn't tell you what it was, you can go ahead and assume that this is covalent, so it makes one particle. Let's go ahead and see what we can do with this. So let's pause this. What comes out of this concentration calculation is that you've got 0.0421 moles of vanillin, so 0.0421 moles of solute, and that comes out to a concentration of 0.841 mole because there's 0.050 kilograms, 50 grams of solvent. That is the total molality because vanillin is covalent and doesn't break up any further. Let's use that now to calculate our delta T of boiling point. Okay, when I use my delta TB equation, I find that the kappa B times the total molality is 1.03 degrees Celsius. Now, what I need you to understand, like we've talked about before, this doesn't mean that the boiling point is 1.03 degrees Celsius. Don't do it, right? I've calculated the delta. That means that the new boiling point is really, let's look at the old boiling point, 78.5 degrees Celsius. The new boiling point is really 1.03 degrees Celsius higher than that. And so taken together then, the TB ends up being 79.5, and technically there's a 3 degrees Celsius. The boiling point got higher when I added solute. I calculated the change and then I added the change on to the old boiling point to get my final answer. These are the most straightforward types of problems, so I want to take a look at a different type where we use boiling point elevation information to learn more about a particular solvent. So in this example, we have ethylene glycol and water. And what I want you to understand is that the water is the solvent, right? H2O equals solvent. Ethylene glycol is the solute. How can I tell there's more water? And we know that the freezing point of the solution, so this is going back to freezing point, it's okay. The freezing point of the solution is negative 6.7 degrees Celsius. So TF equals negative 6.73 degrees Celsius. By the way, this is why you put antifreeze in your car. Adding antifreeze makes a solution. Solutions are harder to freeze than pure things. And so the water in your radiator, because it's in solution, is harder to freeze in the winter, which is good for your car. So I know my TF, which actually means that I know that my delta TF is 6.73 degrees Celsius, right? My goal is to find the molar mass of ethylene glycol, which means the moles of ethylene glycol in, or sorry, molar mass, I have this backwards, the grams of ethylene glycol in 1 mole of ethylene glycol. Things that I know already. Well, I know that this particular setup involves 1,000 grams of ethylene glycol. I also know that delta TF is equal to the freezing point depression constant times the total molality. And total molality is, moles of solute per kilograms of solvent. So does it make sense that if I could figure out the moles of ethylene glycol from the delta TF, I could figure out the molar mass? Let's try it. Let's try to solve. And I'm going to need to look up the kappa F of water. And we've seen this in a previous video, but this is something I would give you. It's 1.86 degrees Celsius per mole. So let's solve our way through this and see what happens. All right, so simple algebra gets us to the point where the molality, which we didn't know, is equal to 3.61 moles of ethylene glycol per 1 kilogram of water. Well, we know that we didn't actually use 1 kilogram of water, right? This is really just the definition of molality. We know that we really used 4.45 kilograms of water. We don't know how many moles that is because we didn't get enough information. That's perfectly fine because now I have a proportion, right? I can cross multiply and solve. And what I find is that X ends up coming out to 16.06 moles of ethylene glycol. Fantastic, because my goal is to get grams in 1 mole, right? I know that I started with 1,000 grams of ethylene glycol. And I know from my calculations from freezing point depression now that that was equal to 16.06 moles. So when I do that, I find that if I take 1,000 grams of ethylene glycol, which is what I started with, and I divide it by the 16.06 moles that I found from my freezing point depression, that my molar mass of ethylene glycol is 62.27 grams per mole. And this is something we do in experiments all the time, right? We can use freezing point depression or boiling point elevation to find the molar mass of something unknown. Let's turn around and look at a related colligative property. The last colligative property that I want to look at in a quantitative way is vapor pressure lowering. And remember that we said that vapor pressure is if I have a liquid in a closed container, there's going to be some gas above it and it exerts a pressure. Things that boil easily have high vapor pressures. Things that don't boil easily have, things that don't boil easily have low vapor pressures. And so when I make a solution, the solvent gets harder to boil, which means its vapor pressure gets lower. And so what we say is that the P of the solution, and so I'm just going to say the pressure of the component, is less than the pressure of the pure solvent. And again, that's from the presence of solute-solvent interactions, making the solvent not want to leave the solution phase. This calculation is different than freezing point depression and boiling point elevation. Because what we do is we consider our components individually, independently of one another. And so we describe our pure components, right? And our components are like A, B, C, so just different compounds. We describe them first by their pure vapor pressure, and we call that P star A, right? So this is the vapor pressure of the pure solvent or solute or whatever it is. And those units could be many things, millimeters of mercury and torr, which are the same thing. It could be atmospheres, it could be kilopascals. There's lots of ways to measure vapor pressure. You don't have to know anything except that it just stays the same throughout the calculation. So we care about its vapor pressure, and we also care about its concentration. And this time it's mole fraction. And when we put this in our calculation, it's the moles of A divided by the total moles. There's a whole video on calculating mole fraction that you want to take a look at if you have trouble finding out and figuring out how this works. But the idea is, and this is also called Raoult's law. So if you ever see this name, it's this equation. The vapor pressure goes down because in solution, there's less than 100% of any compound, right? By definition, it has to be less than 100% because it's part of a whole. So the chi is less than 1. And so because of that, PA has to be less than P star A. It's an easy calculation though. So let's try an example. So we're going to mix. We're going to mix two things together. We're going to mix toluene and benzene. And what do we want? We want the vapor pressures of toluene and benzene. And we also have pure vapor pressures. So let's think about this. Let's think about the fact that the vapor pressure of the toluene is going to be equal to the mole fraction of the toluene times the pure vapor pressure of the toluene. And similarly, we can do the same thing for benzene. We know some of these things already, right? We know that the pure vapor pressure of toluene is 28.4 millimeters of mercury. And we know that the pure vapor pressure of benzene is 94.8 millimeters of mercury. So it looks like it's all about the mole fractions at this point. So let's figure out what the mole fractions are. And remember, mole fraction of toluene would just be moles toluene over total moles. And mole fraction of benzene would just be moles benzene over total moles. The total moles is the same in both solutions. So let's do a couple quick calculations and see what we can do. It's going to involve two pieces of information this time, molar mass and density. So let's see what happens. So if you use the density and the molar mass as conversion factors, you'll find that you have 0.096 moles of toluene and 0.110 moles of benzene. And so of course, if I add those two numbers together, you get 0.206 moles total. So those are our mole fractions. And if I take 0.096 divided by 0.206, I find that the mole fraction of toluene is 0.466. And then 0.11 divided by 0.206 is 0.534. Good. I have two components. And if I were to add up those mole fractions, 0.466 and 0.534, they'd add up to 1. They'd add up to 100%, just like they're supposed to. Now I just plug those mole fractions in, 0.466 and 0.534. And I finish my calculation. So 0.466 times 28.4. The vapor pressure of the toluene in solution, this particular solution, is 13.2 millimeters of mercury. That's lower than the pure, so that's good. Over on the benzene side, 0.534 mole fraction times 94.8 says that the pressure of the benzene is 50.6 millimeters of mercury. And those, the pressure of the toluene and the pressure of the benzene, are what was asked for in this problem, right? Raoult's law is a very easy thing to do once you get it. It's the mole fraction, remembering to calculate the moles individually and then the total moles. That's a little bit of a trick. But if you can convert grams to moles and if you can use density as a conversion factor, you're all set.